Okay. Data is a critical resource that needs to be protected and secured, and people will encrypt that at rest. Sometimes it's encrypted in motion, but what rtegrity is looking at is how we can use Cherry-enabled storage stack to protect that data in use. SPDK is a set of libraries that coexist with the application. So there's a potential vulnerability there. Because the SPDK stack could corrupt the application. Sorry, yes, I'm being pointed out, I'm not using the microphone. The SPDK stack could corrupt the application, or vice versa. The application can damage your storage stack. What we want to do is to isolate them, and ideally, isolate SPDK from its dependencies. So some background for you. SPDK consists of tools and libraries for writing user space storage stacks. It's cutting edge. It uses the latest NVMe features. It's polling to give you maximum performance. And it's production quality. It's actually deployed in several mainstream storage products. It's highly performant and scalable, and that's using a lockless design with threads per core and data structures that are cache aligned and packed. It's also optimized heavily for CPU features. Okay. It makes extensive use of the platform, including shared memory, multiple allocators, physically contiguous memory, and support for a whole load of hardware accelerators as well. It is a large code base. It's about 4 million lines of code, including the dependencies, and there are about 7 dependent projects that are pulled in as part of SPDK. It is all open source with a permissive license. And the good news is there's already a PureCap port of it available on GitHub. So that's where we started from. First thing, choose the compartmentalization boundary. Where are you going to put that transition? Because there's an overhead. As you make the call, so you're paying a performance cost in order to gain the extra security. SPDK has about 250 libraries, and that's too many to do an attempt to hit them all at once. The other thing I would say is library compartmentalization at the point we started is still experimental. It works, but it is still being developed. There is documentation, but it's early stage, although there are some good papers that have been written. And there's not a lot of example code out there to work from. Okay, so first step, created a simple test program just to experiment. So it's a simple application with 3 libraries that are pulled in, 2 of them linked, 1 of them dynamically loaded. And that allowed us to probe the function calls and how the variables work across boundaries. It allowed easy experimentation because basically you take one executable and you just run it with a different runtime linker, and that gives you your compartmentalization. One thing I spotted as we were working on it was that Cherry is absolutely brilliant at finding coding issues. There were times where I wasn't paying enough attention, and it just highlights the issue straight away instead of causing corruption later on that you need to investigate. But how do you know you're actually getting the isolation that you're looking for? We created Cherry Tree, which is a library to allow you to investigate what capabilities are in use. It saves the current register values and the stack, and then prints a capability derivation tree for you, so you can see what you've actually got in the context that you're running. It's linked in with the application, so you need to change your code in order to call the routines. The idea behind it was that we wanted a programmatic way of being able to say what information have I got leaking from a different compartment. That was designed to work with either Linux or Cherry BSD, and it's open source out on GitHub. Okay, that's just showing you. You can see the various values of the registers, and at the top of the screen, there's part of a tree as we're probing down through the memories that is accessible, looking for more capabilities. Okay. Next step, how do you test it? We want an IO generator as a harness. FIO is a good tool to use for that because it provides you with a ready-made storage application, but there wasn't a port. So we started off porting FIO to PureCap. I think there were 3 lines of code that needed changing. Very straightforward. Again, that's out on GitHub. An SPDK has built within it an FIO plugin where the SPDK libraries are joined together, and then the FIO front end talks to those libraries. So that gives you a natural boundary. There is a way of building that so that SPDK consists of multiple libraries, and I'll reference that later on. Okay, performance testing, which was one of the prime goals to see the impact. Obviously, library compartmentalisation adds a performance cost because you need cycles for processing the transition. But for I/O, we're not so interested in how many CPU cycles have gone. We're more interested in what the impact on the latency is and the impact on the throughput. So the stack was tested against a RAM disk. That avoids any kernel transitions, pretty much, and with a small block size, so that what you're really measuring is the cost of an individual I/O. And that represents the real-world worst-case type scenario. Typically, I/O is 4K minimum. Okay. Again, library compartmentalisation is experimental. There were issues, we expected them. I want to say that Depeng has been brilliant at responding to those issues and resolving them. It's been really good. So there were a few things like some undocumented use of a library path. We hit a deadlock, loading dependencies, exceptions accessing thread local storage, calls within a library, actually no library transition involved, but they were going through the trampoline code as well, and that was causing some problems. The other thing that's coming in the next release is that registers that weren't being used weren't being cleared in the version we were working with, and there wasn't an easy way of tracing the transitions. So there was one workaround that we've had to do, which is current code does not support more than 8 arguments. And that meant changing the signature of those functions to use variadic arguments and then pulling them out with va-decl and va-arg. How do you find them? There's a little bit of scripting there that will allow you to look at the function prototypes and pull out anything that would be affected by that. Okay, there are still some outstanding issues. Calls through function pointers are not supported. And that's actually a very common idiom for I/O environments where you issue a request and you have a completion function that gets called at the end of the I/O request. Stack traces don't work across library compartments. That is a pain in the neck, frankly, when you're looking at things thinking, how did it get here? And you get 3 lines of stack trace and it disappears into nothing beyond that. And the other thing that I've hit twice is both SPDK and FIO use shared memory and want to put capabilities in it. Now, you can argue the security disadvantages of doing that, but it's something that needs code changes. How I got around it on this was simply comment that out and not use the shared memory compartment. Okay, here is a brief demo, which will show you, all being well, some performance results as we run. And you can see the average latency with and without compartmentalization and the I/O throughput here. And we're seeing about a 5% difference. What you see further down is the red issue is that when we build SPDK with multiple libraries, we are calling through a function pointer which is in a different library. And so there's a compartment transition required on the I/O completion. And it's failing, as we expect. The thing that does need more investigating is the fact that it works on debug, which I can't explain yet. Okay, so some conclusions. Library compartmentalisation in general just worked. It was very easy to use. It was good. Real world performance impact, I saw about 5%. That's not a rigorous result. It's purely based on the storage stack that we were looking at. And I would say that the code has not been optimized yet. And there is a new release coming out that will have different performance characteristics because it's also clearing out registers that are not used or capabilities that are not used. It does show significant potential, I think, to protect both the application and the storage stack from each other. And you can see the changes again out on GitHub. Okay.
Nick, thank you very much. Any questions at all in the room for Nick? Comrades? Oh.
Hi, Nick. I'm just wondering that being aware of the next release, will you repeat your experiments?
I really wanted to before I got here today, but if there'd been a simple binary, I would have gone for it, but I was time-wise constrained on rebuilding the kernel, so I didn't do that. Sure. But I would love to know because, as I say, clearing out the capabilities when you do the transition, one of the things that I was hoping with Cherry Tree was to be able to programmatically trap what was leaking, but because unused registers are leaking capabilities, that became hard to do. So I would like to look at that with the next release, yes.
Okay, and a second question, in the next release, the library-based compartmentalization model will also work with the benchmark API, which you probably know is the correct way to benchmark software on RMRL.
Yep. Would
you be eager to also repeat those experiments with newer features in compartmentalization and the benchmark API?
Yes, I looked at that. The only slight issue there is that the storage stack is not making system calls in the main because it's from a driving application straight the way down through an in-memory stack. So I wasn't sure that the benchmarking API was going to make any significant difference on the results in that scenario.
Okay. It should make a difference in case you have a lot of calls, because as we talked about, one of the overheads is associated with the branching itself. So it should also make a difference. Okay, thank you.
Yep.
Thank you, comrades. Any other questions from anybody else?
I have a question.
Oh, yeah, go ahead.
Looking more long term, how do you see this work integrating into the future, your future work? What do you see the next steps to be?
I think there is a challenge with Cherry in terms of getting a viable ecosystem that will drive adoption. I very much like capability-based design. I worked years ago on the CAP computer at Cambridge, and I've always believed in the technology. I really want to see it mainstream. I don't know where it's going to go, to be honest, because there is it's a non-trivial exercise to go from where we are to where we want to be. Does that answer your question?
Any other questions? I do have one. It may be a silly question, but do indulge me, please. Comrades was asking about, obviously, whether you would look to bring in kind of the next release of Cherry and then kind of do testing again. On the previous slide with conclusions, you had a point around kind of optimizing the code. If you were to just do code optimization before kind of updating to any new releases, do you have any sense at all of what performance you may see, or is that a silly question to ask at this point?
Actually, the optimization I was referring to was the dynamic linker, the library compartmentalization optimization, rather than the SPDK stack. What I was looking at really was taking the off-the-shelf standard SPDK stack and seeing whether it was viable to apply library compartmentalization to it in terms of performance impact.
Cool. Thank you for clearing that up for me.
Sure.
Any other questions at all? No? Nick, thank you very much.
Sure.